Today we are going to learn about using structure to reason about the number of solutions an equation has. Then you will solve a variety of linear equations with one solution, no solution, and infinite number of solutions. By the time you walk out of the door today, you should be able to determine whether an equation has no solution, one solution, or infinitely many. We will continue on this concept in lessons to come, where you will continue to solve equations even further. Let's take a look at the first activity, which is on page 32 in your workbooks. Please open up to page 32 now and look at the example titled, "Which One Doesn't Belong? Equations." At this time, I'd like you to pause the video and make an effort to determine which of these four equations doesn't belong with the others, and think about why. Pause the video and write your answer and responses down now. Let's check your responses with mine. In actuality, you could have determined that any of these four equations don't belong. So based on what you chose, see if it matches my response. If not, go ahead and add to your notes at this time. Someone may say that equation 1 doesn't belong with the others because it is the only equation that involves addition. Someone may argue that equation 2 doesn't belong with the others because it is the only equation involving multiplication. Someone else may argue that equation 3 doesn't belong because it is the only equation with only one number on the left-hand side of the equation. And lastly, with problem number 4, someone may argue that this equation doesn't belong because it is the only equation that involves it is the only equation that is actually not true. If you go ahead and perform the operations in all the above equations, 5 plus 7 is 12, and 7 plus 5 is 12, which is true. If you perform the operations in equation 2, 5 times 7 is 35, and 7 times 5 is also 35. So they are equivalent, which also makes them true. If you perform the operations in problem number 3, 7 minus 5 is in fact 2, which is equivalent to 2, so again, is true. However, if you perform the operations in equation 4, 5 minus 7 gives me negative 2, where 7 minus 5 gives me positive 2. These two are not equivalent. Therefore, this is not a true statement. So in problem number 4, we could argue that this is the only equation out of the 4 that is not true. At this time, if you don't have responses, add these into your notes. You may have different responses as to why you chose an equation that doesn't belong, but please go ahead and add these into your notes at this time. Once you are done, you can resume the video and move on to the next example. We're about to do another activity which involves thinking about solutions. We started to do this with problem number 4 in the which one doesn't belong equations. Let's do a couple examples together before you go on your own and attempt some equations. These next examples are actually not in your workbook, so you should hopefully have some space at the top of page 32 where you can add these equations in and show some work to go along with it with me at this point. So please write these equations down at the top of page 32 now. Let's take a look at the first one. It says, find the value of t that makes this equation true. So essentially, there's a few ways we can go about this. You could start testing numbers and see what happens, or you could attempt to start solving this equation. If I wanted to start solving this equation, and let's say I wanted to group my 5's together, I would go ahead and do the inverse of a plus 5, which would be a minus 5. So 2t plus 5 minus 5 equals 2t plus 5. And again, I need to balance my equation. If I subtract 5 from the left, I must subtract 5 from the right. When this happens, we get our 0 pairs on both sides. And now we're left with 2t equals 2t. Hopefully what you are realizing, and you may have even realized it at the start of this equation, is that the left side is exactly equivalent to the right side. So it has already been balanced from the very start. We can further see this after subtracting the 5 from both sides. Originally, we were left with 2t plus 5 equals 2t plus 5. Now, after eliminating the 5's, we are still left with two equivalent statements. 2t equals 2t. These statements will always be true. If I wanted to go ahead and eliminate my 2 now, I know I can do the inverse, which I'm seeing 2 times t. The inverse of multiplying would be dividing. So I'm going to divide by 2, and again, whatever I do to the left, I must do to the right to balance my equation out. On the left, they divide out. On the right, they divide out. Now I can see even further that I'm still left with two equivalent statements. T will always equal t. So when this occurs, this means that I can pick any number I want in this problem, and it should always make the equation true. If you're not sure about that, start testing some numbers. For example, if I wanted to substitute 1 in for t, let's see what happens. 2 times 1 plus 5, will that equal 2 times 1 plus 5? When I do the math on the left, 2 times 1 is 2. 2 plus 5 gives me 7. When I do the math on the right again, 2 times 1 is 2 plus 5 again gives me 7. So we can see that 1 works as a value of t. Go ahead and pause the video right now and test a couple more values. You may want to try 0, you may want to try a negative integer like -3 or -5. So go ahead and pause now and try and test a couple more. Hopefully what you realize, no matter what number you tested in for t, they all hold true. 2t plus 5 will always be equivalent to 2t plus 5. Or, once we do the inverse operations, in the end, we get to t always equaling t, which is in fact always going to be a true statement. So what this example tells us is that we can choose any value for t that makes the equation true. So, all values work in this equation. Again, please make sure you have this example written somewhere, hopefully at the top of page 32. Now let's take a look at the second example. Find the value of n that makes this equation true. N plus 5 equals n plus 7. Well, if I compare this example to the previous one, I notice they are not two equivalent things on both sides of the equation. I do see that n and n are balanced on both sides. However, I have a plus 5 and a plus 7 on each side, which are not exactly the same. So some might notice right here that there will be nothing I can input for n in order to balance these out and make the equation true. But if you did not notice at this point, again, we can continue with our inverse operations. If I wanted to combine my 5 and my 7 together, I can do the inverse of a plus 5, which again would be a minus 5. And whatever I do to the left, I know I must also do to the right, again, to balance the equation. My 5's make a 0 pair on the left, and on the right, when I do 7 minus 5, I'm left with 2. We can still see that this equation is not balanced. If I wanted to further solve this and group my n's together, I can do the inverse of this n over here of a positive n, which would be a negative n. So if I were to subtract n from both sides to make a zero pair on the right. Again, I need to do that operation on the left to balance my equation. We've got our zero pair. We've got a zero pair here as well, which leaves me literally with 0 since I have nothing left on the left side. And now I'm left with a statement such as 0 equals 2. This statement we know will never, never be true. So because throughout this process we were seeing untrue statements, we can conclude that no matter what we put in for n, this equation will never be true. Again, pick a number and test it. Let's test -1 this time. So if I were to input -1 for n, so we're checking with -1, will these two statements be true? Well, if I add -1 plus 5, I get 4 on the left. If I add -1 to 7, I get 6 on the right. We know that 4 can never be equivalent to 7. So this just further proves that this equation has no solutions that will make it true. At this time, why don't you go ahead and pause the video again and test a few more numbers, maybe 0, maybe a positive, maybe another negative integer, to see if you can find anything that will make the equation true. After testing those numbers, hopefully you realize that there are no values that will make this equation true. Now that we've done a few examples together, I'm going to ask that you go ahead and pause the video and complete the examples in the middle of page 32, where it says thinking about solutions. It is your task to sort these equations into two columns. One that will contain all values or all possible solutions for the equation. And the second column, or the second category, should contain the equations with no values. Think about the approaches we just did together with the last example. If you can recognize it early on without having to go further with the math, that's fine. If you need to take it all the way to the end and complete all your inverse operations to see whether the two are equivalent or not, that's fine as well. So pause the video now and go ahead and complete your sort. When you're done, you can check it with mine. Welcome back. Let's go ahead and see how your sort went. If we take a look at the first example given to us in your workbook, n equals n. I'm going to place n equals n in the all values column. This was very similar to the last example we did together when we got t to equal t. So if n equals n, I know that is a true statement. No matter what I put in there, no matter what number we input, we will always get the same output on both sides. Let's take a look at the second equation. 2t plus 6 equals 2 times the quantity of t plus 3. I'm also going to place this in the all values category. If I were to do some math to prove that all values would work on the right-hand side, I know I can distribute my 2. So let's go ahead and do that now, if you haven't done so already. I know with distributing I'm multiplying, so 2 times t on the right gives me 2t, and 2 times 3 gives me 6. I can clearly see at this point that these are two equivalent expressions on both sides. 2t plus 6 will always equal 2t plus 6. So if you noticed it at this point, you don't have to go any further, and you can stop here and place it in the all values category. Let's take a look at the one below. 3 times the quantity of n plus 1 equals 3n plus 1. I'm going to go ahead and place this in the no values category. Let's prove why this one has no values that will work. Again, I'm going to use that same concept as I did in the last problem. I know I see a 3 outside the parentheses, so I can distribute it. 3 times n gives me 3n, and 3 times 1 gives me 3. Some of you may notice at this point that it belongs in the no values category because it's not completely equivalent on both sides. Yes, I have 3 n's that are the same. However, this plus 3 is not equivalent or balanced to this plus 1. So if you noticed it right then and there, you could stop and place this equation in the no values category. Let's have a look at the next equation. 1/4 times the quantity of 20D plus 4 equals, excuse me, equals 5D. I'm going to again place this one in the no values category. And if you're not sure why it belongs in the no values, let's go ahead and do some math to prove it. Pardon me. Just as the other two examples, I know I can use my distributive property again on the left-hand side of the equation, and I can distribute the 1/4. Remember, multiplying by a 1/4 is the same as dividing by 4. So if I take 20D and divide it by 4, I will get 5D. If I take 4 and multiply it by a 1/4 or divide it by 4, I get 4 divided by 4, which is 1 whole. On the right side, I just have 5D. So notice the 5Ds are equivalent. However, this left side has a +1 after distributing, and there is no +1 on the right side. So these two will never be equivalent or balanced. Therefore, there are no values that will work in this equation. Let's go ahead and take a look at 5 minus 9 plus 3x equals -10 plus 6 plus 3x. I'm going to go ahead and place this equation in the all values category. Let's take a look at why this equation works in the all values category. If I looked at the left-hand side of the equation, I know I can further combine like terms, meaning I can do this math here of 5 minus 9. When I do 5 minus 9, I get -4 plus 3x on the left-hand side. I also know on the right-hand side, I can do this math and combine -10 with 6. When I add -10 with 6, again, I get a -4 plus 3x. Hopefully at this point, we can see that both sides of the equations are balanced and they have the exact same terms. So therefore, no matter what I input for x, it should always work. That's why it belongs in the all values category. Let's go ahead and take a look at the next example. 1/2 plus x equals 1/3 plus x. I'm going to go ahead and place this one in the no values category. Just as the other examples above, I actually don't even have to distribute because there's no parentheses, but I should be able to tell that these are not balanced on both sides. Yes, they both do contain an x, which makes that portion balanced. However, I know that 1/2 will never be equivalent to 1/3. Those are two different numbers. So if you recognize it right then and there, we can stop and say, oh, that belongs in the no values category. Remember, if you're unsure about any of these and it's not making sense, you can always pause the video and test and input numbers to see if it holds true or not. For example, with this problem, if I wanted x to be 1, I could input 1 for x. And when I add these two together on the left side, I get 1 and 1/2. If I input 1 on the right and add 1 with a third, I get 1 and 1/3. I know that 1 1/2 will never be equivalent to 1 and 1/3. So you can always do that and test any integer or any number at all in any of these equations if you're unsure of why it belongs in which category. Let's go ahead and take a look at y times -6 times -3 is equal to 2 times y times 9. I'm going to go ahead and place this one in all values make this equation true. And let's take a look why I would place it there. Again, just like I worked out the previous problem above in this category, we can go ahead and combine some integers on the left-hand side. I can do the math of -6 times -3, and I get a positive 18. I can do the math on the right with 2 times 9, and again, I get a positive 18 times y. We know based on the commutative property of multiplication that y times 18 is in fact equivalent to 18y. So therefore, both sides of the equation are saying the exact same thing and are completely balanced. So no matter what I input for y, this equation will hold true. So all values work. Let's go ahead and check the last equation. V plus 2 equals V minus 2. I'm going to go ahead and place this one in the no values column. Hopefully, you're noticing the pattern or the relationships here. Yes, again, we have the two equivalent V's on both sides. However, we should realize that a positive 2 will never be equivalent to a negative 2. So therefore, this will never be balanced. So no matter what we input into this equation, no value will work here. At this time, please pause the video. Make sure you have all of your equations in the correct columns, and you've shown some math like I have in red and blue here to prove why they belong in that column. If you need to add to your notes now, please do so. Again, if you're still unsure as to why these equations belong in each column, test a few more integers in each one to make sure that either all values work in the left-hand column or no values would work in the right-hand column. Let's go ahead and take a look at questions 2 and 3 now at the bottom of page 32 in your workbook. Question 2 is asking you to write the other side of this equation so that the equation is true for all values of u. Question number 3 is asking you to rewrite the equation on the right-hand side so that there are no values that for u that makes the equation true. At this time, please pause the video and attempt to do this on your own. When you are done, you can check your equations with mine. Please remember there are multiple equations that could work in both situations. So if you do not have exactly what I have, go ahead and test your equations over and over with multiple integers, positive, negatives, 0, to make sure that yours work. Here's what I came up with for question number 2. I went ahead and wrote out the right-hand side of the equation to be 6u minus 10. So I am making this equation true for all values of u. To prove it, let's do some math on the left-hand side of the equation. If I were to distribute 6, I get 6u minus 12, then plus 2. When I combine negative 12 plus 2, I get 6u minus 10. Which in fact is equivalent to the right side that I created of 6u minus 10. So you may not have 6u minus 10, you may have 6u minus 12 plus 2. That would work. You may have 6 times the quantity of u minus 2 plus 2 rewritten again on the right-hand side. That would work as well. So whatever you do have on that right-hand side, please make sure that it balances out with the left, and you can again test it by inputting numbers. Or you can use my example if you were unsure. Let's take a look now at example number 3. This time they wanted us to create an equation that would make no values of u work. So here's what I came up with for the right-hand side of my equation. I simply just put 6u. I know that this won't work because after simplifying the left-hand side of the equation above, I know it becomes 6u minus 10. Which is not equivalent to 6u. I have my minus 10 on the left, but there is no minus 10 on the right. So therefore, I know if I use 6u on the right-hand side of my equation, it will not be equivalent to the left. Again, you may have came up with a different one. Please double check and make sure that yours is valid. If you're not sure, check more integers or go ahead and write mine down along with yours. Let's think about a few questions after completing this activity. Why did you sort the equations in the all values column? At this time, if you could please write your thoughts down to these 2 questions at the bottom of page 32 where there's a little bit of workspace down there. So why did we sort the equations into the all values column? Well, hopefully what you realized is that both sides of the equations were always balanced or equivalent. Since that was the case, we knew that any number would work for that variable. So if both sides of the equation are equivalent or the same, then any value for the variable will make the equation true. Again, please write this statement down at the bottom of page 32. On the flip side, why did we sort the equations into the no values column was exactly the opposite. If both sides of the equation are not the exact same, then no value will make our equation true. After you're done writing this down, we're going to go ahead and move on to the next activity or the next example, which is what's the equation? This is located on page 33 of your workbook. So in this activity, they're asking us to complete each equation so that it is true for all values of x. So we want to think about that whole left side being equivalent to the right side, making all values true. Please pause the video and attempt these 3 examples on your own first, and then resume and check them with mine. When I look at example A, I notice on the right-hand side there are some parentheses. So if I think about distributing here, and remember, I want it to be balanced and equivalent to the left-hand side. If I do 3 times x, I get 3x, which is in fact the same as what's going on the left side. Now I have to think about 3 times what number here will get me to 6. Well, I know 3 times 2 is going to get me to 6. So if I just simply place a 2 in that missing place, I will have 2 equivalent equations because 3 times 2 is in fact 6. So we can see now that the left side is equivalent to the right in this equation, so therefore any value for x will hold true. I can use that same approach in example B. Even though there's not a number outside of the parentheses, we can do the distributive property with a negative sign. So I'm going to first distribute to my negative x over here. If I take a negative times a negative, I'm going to get a positive x, which now I can see a positive x on the right and a positive x on the left. All I need to come up with now is that -2 or that -2. So I know, again, if I put a 2 in the missing spot here and I were to distribute my negative sign to my 2, that will become a -2, which -2 or -2 mean the same thing. So now I can see I've made an equivalent equation on both sides to show that any value for x would work. Remember, x minus 2 is in fact equivalent to -2 plus x. So by simply placing a 2 in the slot for B, in the missing blank for B, I have created an equation where all values of x will hold true. Let's look at example C. It looks slightly different than the others. In A and B, we use the distributive property. In example C, we can still distribute, but rather than multiplying, we're showing a fraction bar, which means to divide. But we can do that same process by, instead of multiplying, we can divide both of these terms on the left by 5. Remember, dividing by 5 is in fact the same as multiplying by a fifth. So that distributive properties can technically still be showing multiplication if you think about it as multiplying by a fifth. I'm going to go ahead and think about it as division though. Sorry, that's very messy. Let me rewrite that. 15x divided by 5 minus 10 divided by 5. So let's complete that math. 15x divided by 5 gives me 3x. And minus 10 divided by 5 gives me a minus 2. So now I can compare these two terms with the right-hand side of the equation. Negative 2 or minus 2 is represented in both. And what's missing is my 3x from the right-hand side to make it equivalent. So I'm going to input a 3x in the blank on the right-hand side. So now we can clearly see 3x minus 2 on the left is equivalent to 3x minus 2 on the right. If you did not get any of these examples, please make sure to input them in your notes along with the work to show and prove why they are equivalent and balanced and why any value for x would make these equations true. Okay, after completing these 3 examples, stop and think about question number 3 here. Asks you to describe how you know whether an equation will be true for all values of x or true for no values of x. So we actually jotted this down. Hopefully you have it at the bottom of page 32 in your notes earlier. You can simply transfer this over at this time, but reminding you that how do we know whether an equation will be true for all values of x? So for all values of x, will tell us that both sides of the equation are equivalent. Or the same. And remember, or reminder, for no values of x, we have discovered that both sides of the equation are not the same or not equal. So again, you should have that in your notes, and if you don't, now's the time to make sure that's written in there. So for all values of x, what did all these answers have in common? Well, as we previously stated, both sides of the equation were always equivalent at some point. Some of us may have found it or discovered it earlier than others. It may have been very simple to see from the beginning. We may have had to do a few inverse operations to see it, just depending upon where you were at. What strategy did we use to figure out what the answer had to be, whether it was all values or no values? Well, a strategy that we used was solving the problem using inverse operations. Okay, so that helped us to balance out our equation to see if the left side was in fact equivalent to the right side. For no values of x, why are there so many different solutions to these equations? Meaning, I'm sorry, let's ignore that question at this point. So we did talk about the second question here. What was different about equation C? Equation C, we talked about why it looked different with the fraction. So we still were using that distributive property. However, we were doing it with a fraction or by dividing as opposed to multiplying. All right. So just recapping again what we talked about, what are some ways that you were able to determine how many solutions there were to the equations that you solved today? We talked about using inverse operations. We talked about looking to make sure the left side balances with the right side. And if they do, we know that throughout all values for x are possible solutions. If they don't, we know that no values for x are possible solutions. In your workbook, you have your lesson summary on page 34. That's where this information comes from. They give you an example. They say an equation is a statement that two expressions have an equal value. The equation is a true statement if x is 3 in this particular equation. So they're proving it by inputting 3 in for x. We know we can actually use inverse operations to also prove that statement. 2 times x, the inverse would be to divide both sides by 2. So x equals...
Good morning, students. Obviously, it's pretty cold out there.
I apologize for that interruption on the intercom. All right, so in fact, we're able to further prove that statement of x equals 3, not by just substituting in, but using our inverse operations. Then it goes on to say it is a false statement if x is 4. If you try to input 4 for x, 2 times 4 will never equal 6. 2 times 4 is obviously 8, which is non-equivalent. They then go on to give you another example. The equation 2x equals 6 has one and only one solution because there is only one number that you can double to get 6. Some equations are true no matter what the value of the variable is. For example, 2x equals x plus x will always be true for any value because I know when I combined x with x on the right, I do in fact get 2x. So please notice the difference between this example versus the previous one. The last example we did has one solution for x. X is 3 and can only be 3. In this example, I can input any number for x because the two sides are balanced, and no matter what I input, I will always get that balance. Let's go ahead and take a look at our third option now and recap our third option for equations, which is some equations will have no solutions. For example, with this equation, x will never be equivalent to x plus 1. Because remember, this has the plus 1, this side does not, so therefore it will never be balanced. And no matter what value I input into this equation for x, I will never get two equivalent sides. So, it is important to realize at this time that that equations can have one exact solution, all values or all solutions, or no solutions at all. Keep this in mind while you are working on your quick progress check for this lesson and your practice problems and problems to come. At this time, please go ahead and complete your quick progress check that you grabbed when you walked in the door today, and make sure to input it into the inbox as soon as you are done with this.